So today we're going to talk about what to do with our DNA fingerprints once they have been run. One of the things that you can do is take a look at the banding patterns that exist. So this is a sample DNA profile that has been run, and so as these fragments of DNA separate based on size, we can see that they end up with these lines that fall into different locations, and these are referred to as banding patterns. Okay, we can see that this line and this line ran the same distance, so we would assume that they are the same size of fragments. And so when we were doing criminal cases, what we will do is we will take a look and try to match up the banding patterns from a victim or a suspect and match them to hopefully the person who did the crime. Today what we're going to do though is that we are going to go through and we're going to take a look at how to analyze this data so that we can hopefully map some genes or some chromosomes and figure out where everything is in relationship to each other. And so the first step in that is to take some fragments and run them through the DNA profile. So I have our sample right here. We see in this lane right here, this piece of DNA was cut with the restriction enzyme HND3. In this second lane right here, we have DNA that was cut with EcoR1 enzyme. And then in this final column, it is cut with two enzymes, HND3 and EcoR1. The R1 kind of rolled over here. And so we have these three samples that we're going to analyze. And in order to do that, what we see then is that we need to have something to compare everything to. And so we use something that is referred to as the standard. And our standard serves as our control for this experiment. And so what a standard is it's a known set of DNA fragments where we know the lengths of each of the fragments, so that when we go through and we run the DNA, we know that the smallest fragments always travel to the farthest end. And so we see down here that this is labeled as 500, meaning that this is 500 base pairs long. And so because our smallest fragments travel to the farthest end, we know that this is the positive end of the gel. And so therefore this is the negative end. Our wells are always found down at the negative end. So in this case, I'm going to use the edge of the square here to represent the well. All right, so we have this standard that has been run so that we can use it as a comparison to the rest of our data. On this example, they've gone through and filled out how long each of the fragments are. Okay, so what do? Well, we go through and we use a ruler, and we really are just going to go through, and because this is science, we're going to measure in metrics. Kind of the general overall rule is that you want to measure from the top of the band to the top of the well. And because this is kind of upside down from what I usually draw, the top is down here because this is where it would travel the farthest. So I'm going to line up the 0 there, and I see that it is about 8 millimeters long. Then I'm going to go through and measure the second one, and my second one is about, if I go through here, it's about 17 millimeters long. All right, and then I'm going to measure my third one down here, and it is about 30 centimeters long. And I am going to continue to measure each and every one of these bands from the top here to the top of the well. I also then will go through and measure the lengths of this band to the well, this one, and each of them in between. And so I will get some data then that looks something like this. Oh, I gotta zoom out. All right, so I should get some data that looks something like this. All right, so now what do? Well, now I need to go through and I'm going to use my standard here, or my marker information, and I'm going to graph it. Okay, but we're going to graph it on a new type of graph paper. This graph paper is referred to as a semi-log graph paper. And so what we see is that here on the x-axis we have our normal increments of 0, 5, 10, where each line represents 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can change these increments here as I will be changing them to fit what we need. So this will be 10, 20, 30, 40, 50, 60, and 70. Okay, but when we go up on the y-axis, what we see is that our numbering system is kind of goofy. And so what happens is that we are starting here at 100 base pairs, and we're going to count by ones in the first section. So it'll go 100, 200, 300, 400, 500, 600, up to 1,000. Now, once I hit this 1,000 mark right here, we now switch our unit, or not our units, but we switch our increments, and we are now going to count by 1,000. So this is 1,000. Instead of the next line being 1,001, it is now 2,000, 3,000, 4,000, up to 10,000. Once I get to my next section, now I'm going to count by 10,000s. So I've got 10,000, then I hit 20,000, 30,000, and 40,000. And so it starts to kind of squish everything together the farther that we go up. All right, so our y-axis is going to represent the number of base pairs that we find in that fragment. All right, so back to my original set here. Again, we know the lengths of these standards. They are given to us by the companies that run this, and so we can go ahead and we know that the ones that have traveled the farthest distance then will be 500 base pairs long. The one that has traveled the second farthest distance will be 1,000 base pairs long, and we can continue to fill in that information. All right, so now we need to graph this. So we will take the distance that the fragment has traveled, the distance in millimeters that the fragment has traveled, and we are going to plot it versus the number of base pairs. All right, so we know that my one base pair traveled 8 millimeters, so I'm coming over here. I've got this labeled as 10. There we go, 10. So this is 2, 4, 6, 8 millimeters. And it is traveled 500, it is 500 base pairs long. Traveled 8 millimeters, it is 500 long. So I'm going to come over here, and I'm going to come up. Okay, I lied. Let's start at the top. All right, the shortest distance, because that's how my graph works. The shortest distance right here is 8 millimeters, and it is 9,000 base pairs long. So this traveled 8 millimeters. There we go. All right. So we go over to 8, and we're going to go all the way up to 9,000. So here's 8,000, and then we have 9,000, and we're going to put our F dot on the plot. Okay. Then we're going to go to the next one, the shortest distance. Here's the well. And this one, according to our measuring, is 17 millimeters in distance. We know that it is 6,000 base pairs long. All right, so I come back to my graph. And so I'm going to go over to 17. So I'm counting by 2. So 2, 4, 6, 7 will be halfway in between here. And it was 17 millimeters, or sorry, it was 6,000 millimeters, or 6,000 base pairs long. So we will put the dot right there. All right, so we're going to go ahead and we're going to continue to plot all of these markers and the distance they traveled versus the base pairs. So we should end up with a graph that looks like this. All right, so now what we're going to do is we are going to create a line of best fit around the base pairs that really tend to follow a pattern. And so, or a mostly straight line. When I take a look at this, I've got all of these in a straight line, and this one's kind of an outlier down here. So really what we're going to do is we're going to kind of disregard this one in terms of our line. And so when we go through and measure this, okay, again, what we are doing is we are eyeballing this information. We don't need to use a calculator to figure this out. All right, so I've got my line of best fit here that covers mostly all of those dots. Okay, so now what we want to do is we want to be able to go through and figure out how long are each of these base pairs. So because we know how long each of the ones are for the marker and how far they traveled, we can go through and we can estimate then by looking at the base pair for the Hindi 3 restriction enzyme that traveled 29 millimeters. We know that it is between 6,000 base pairs long and between 3,000. So we can now take that information and go to the graph. And so we would go over here on the x-axis to 29 millimeters, okay, which is right here. And we are going to go up and follow our line halfway up to where it crosses our line of best fit. Then we are able to come over. Let me see if I can do this sideways. Could use a ruler. I think that's straight. All right, so it's about straight. And we see that here's 2,000. This is 3,000. We're about halfway through. So we're going to say it's about 3,500 base pairs long. Okay. In order to figure out the next one, we would go to 52. So we're coming over to 52, which happens to be on this line right here. All right. And we come over, which happens to be our other plot, so we can see right away then that is right at 1,000. All right. So we have this one as 1,000 base pairs long. And then we would go ahead and we would continue to map out each of these additional links in that manner. Okay, so what are you going to do? On your worksheet that you will get a semi-graph log paper. You also are going to have a paper that looks like this. Your Hindi 3 digest is serving as your standard. All right, and we have been given the different lengths of each of the base pairs. So depending on how your gels turned out, you may or may not have all of these bands. And so we'll have to go ahead and take a look at that. And so you are going to go ahead, and the first thing I want you to do is take a picture of your DNA fragments, and then you are going to print those pictures out, and you will tape them into the slot on your packet from online. Okay, so I want to see that. Sometimes that's actually the best way to measure your DNA fragments, is to go ahead and take a picture and then measure off of your phone. Just make sure that you're always at the same zoom in segment when you're measuring all of the band fragments. Or you can measure right off the gel, but I do want to get a picture of that. You may have to, if your DNA fragments did not turn out, you may have to actually go through and use somebody else's that did turn out. And if they're all kind of icky, I will give you some sample data, or I will give you the real data of what you should have seen, and then you can base the fragment lengths off of that. Okay, so with your Hindi 3, these are the different fragments, and so you will go through, you will measure the distance that each of the bands have traveled, and you will record it in this column. Okay, you will go through, and then you will measure all of the bands that showed up, and you will put them, the distance traveled, in the ECO R1 column for the distance, and then you will do the PSTL, and then you will do the single uncut lambda DNA, and this should only have one band, okay, because it's uncut, so it's just one solid piece of DNA. You are not going to have 6 different bands for every single restriction enzyme, but there were 6 that should show up, hopefully, if we put enough DNA into the standard. So you will go ahead and measure each of these columns, and then you should be able to plot your information. You will plot the Hindi 3 onto the semi-log graph, and then you should be able to estimate the base pair lengths based off of that graph. Okay? All right, and I hope that you have a great day, and this makes sense to you.